Morning, everybody. Welcome to class 31. What time is it here? 11:10. So welcome. There's 262 of you on the call. So good to see all of you. I'm going to share my screen here to kind of go over what we're doing. So what I've got going on is we're actually finishing up chapter 10. So this is solving simple harmonic problems, simple harmonic motion problems, damped vibrational motion, driven vibrational motion. So there was a question in the chat window that I'm just remembering right now that was asking about the final exam, which is on December 17th at 7 p.m. Will it sort of cover all the chapters equally? And so the answer to that, I think I misspoke before, it is sort of an even spread over the whole course with a slight emphasis on chapter 11, which is the final chapter we're studying this course, because there was no midterm that covered any of chapter 11 stuff. But yeah, all chapters 1 through 10 are sort of evenly spread, or 2 through 10, I guess. I don't think there'll be really a chapter 1 question. Okay, and let me go through couple more slides here. I think I want to start actually with a poll question. There's going to be a few poll questions just to get used to this, multiple choice questions, like tomorrow night's multiple choice stuff. Two pendula have the same length but different mass. So that means that the force of gravity is larger for the larger mass, because force of gravity is mg. Which will have the longer period? Grab my pen here. Remember, these are pendula. Okay. I'll end the polling. Share results. Well, let's see. This is sort of a trick question. So if the length of the pendulum is L, then the period is equal to 2 pi times the square root of L over G, I believe, right? So the longer L, the longer period, but the mass is doesn't matter here. Does not matter in determining the length. And so this is assuming simple harmonic motion. This is assuming that the string has negligible mass compared to the mass that's on the end. This is a big M, this is a little m. Certainly, for those of you who answered A, it is true that if it's a mass on a spring, where the outside force is coming from the spring, then the larger mass will have a longer period. It would have been A there for mass on a spring, if that's kind of what you're thinking. But in terms of a pendulum, the idea is that the force that's actually driving the simple harmonic motion is the force of gravity. So if you increase the mass, you increase the inertia, just as you would with a mass on a spring, but you also increase that restoring force. And so those two effects cancel each other out, and the larger mass has the same period. Let me make sure I have my chat open here. So where is the chat? Behind another window. Simple harmonic motion is an assumption here, I guess, yeah. So it'd have to be less than 10 degrees and a lot of stuff. Where's my participants? Just look for raised hands as well. Okay. So this is what it sort of looks like. So the condition for simple harmonic motion is, for a pendulum, is that there's these small angles. So if you look at sort of the maximum sort of amplitude, delta theta max should be like less than around 10 degrees, else it's not going to be simple harmonic motion. The condition for simple harmonic motion for a mass in a spring is that the spring has to obey Hooke's law. So any spring will obey Hooke's law if you just push it or pull it a little amount. But if you overstretch the spring or compress it too much so that the coils actually touch, then it no longer obeys Hooke's law, and a mass on the end of that spring will not be simple harmonic motion. But if those are the cases, then here's the equations for period. So the period for mass on a spring, square root of m over k times 2 pi, and period for pendulum, square root of L over K times 2 pi. There's a lot of chatter going on in the thing. I think I did post these, but only about half an hour ago, the notes. Jerry, did you have a question?
Yeah, it's not a academic related question. I'm just wondering if there is a formula sheet provided for us.
No, so it's a, but I mean, it's a completely open book test, right? So I would write out some equations on a piece of paper that I thought were useful, like these ones, just to have my notes handy. Emanuela?
Hi.
Hi.
I wanted to ask about the small angle. I didn't quite understand the explanation for why it wouldn't work for a bigger angle. And in any case, when a pendulum is swinging, doesn't it like change angles like as it's swinging at the top?
Yeah, definitely. Yeah. So that delta theta is sort of like the x, right? It goes back and forth, and so it's a equal to whatever the amplitude times cosine. But the amplitude has to be less than around 10 degrees. And what happens is that, I don't know if you can imagine even like a pendulum where if this was the pivot, if it was standing straight up, I don't know if it was on a string, instead of a string, maybe a really thin like rod, then it could just sit there forever, right? It wouldn't actually be in simple harmonic motion. You'd have to perturb it a little bit and it would go, you know, a little bit like this, and then it would swing around like that. So that's not simple harmonic motion. So there's some limit, and the limit is that it has to be within around 10 degrees of this center of hanging straight down, or else the force cannot be. You can't use the small angle approximation of sine theta is roughly equal to theta.
Oh, right. Okay, thank you.
Okay, sure. Good questions. Okay. Announcements. Oh yeah, this is just this. I was wearing the same shirt on that crazy Friday, October 30th, and now it's November 30th. So there's my November. You should have received an email from these Lasso people. Sometimes looks like learning assistants. I can't remember what it all stands for. So this is that there was a pre-test, which was there's two. One in force concept inventory about physics, 30 physics questions, and then the other one's called class. It's about learning attitudes in science. Sort of more of a survey question about whether you agree or disagree with certain statements. Okay, and now you're kind of doing this. You might recognize the questions are very similar, the post to the pre, but now I guess the question is, have you sort of gained anything or changed your attitudes or changed your feelings about science or about physics from taking this course or not? So I would like you to take that. Again, to encourage you, you get 1 homework credit for doing each of the tests, but you've already had 2, so total possible of 4. And it's all just for participation, not for accuracy. But I would like you to try your best. And yeah, I'm going to shave this thing off tomorrow morning. So that's my wife really hates it, so got to do it. I like it, but what are you going to do? Ilian, question?
Yes. Hi.
Hi.
So about the pendulum period, you said that was for smaller angles.
Yes.
So how would it work with larger angles, or would that be sort of like beyond this course?
It's definitely beyond this course, but it's a good question. The answer is it's greater. And the reason is that the force ends up being less than theta if you get too far up. Like I was saying, is that if you're staying straight up and down, it would take forever. Right? The period would be forever if it was theta was equal to 180 degrees, right? The initial or something. And so, and in between there, it's somewhere between that period that's given and a little bit, it approaches infinity as you get up towards the top. But again, that's beyond, and it's not simple harmonic motion. let's do another poll here. Here's a kid on a swing, and the question here is, what's the difference between sitting on a swing and standing on a swing? If you could sort of imagine that, would it change the period? Where's my poll here? Poll, sorry. Okay, so there's your poll. A is that the period of the swing oscillations is greater, B the same, or C smaller. And again, let's assume simple harmonic motion. It's a bad diagram there. Okay, let's see what survey says. A lot of people are saying smaller period. Yeah, so wait, so the way the equation is, remember that the period is equal to 2 pi times the square root of, what was it again? Sorry, I'm forgetting. L over G, right? Longer L means longer period. So what I'm going to do is will be L effective. Okay, is I'm going to say the distance between the axis of rotation and the center of mass. That's my idea here. Yeah, so I like smaller. So the center of mass would be sort of, you know, in the middle of U, right? So this is the distance right here, L. Okay, so standing would actually shrink the L. So L is smaller. Stand up. Does that make sense? 53% of you got that one. Very good. Should do another one. Oh, not yet. Oh, sorry, I did want to do one more. Okay, a grandfather clock, which is calibrated at sea level, is now operating in Calgary, Alberta, which is 1 kilometer above sea level. This clock runs. So this all depends on the period of the swinging motion. And if it's even just a little bit off, you will have a clock which runs fast or slow. Think about this one. Again, we're going to assume simple harmonic motion. And let's write it down. Okay. It's a bit of a hard one. Do you guys want to click in? 5 seconds? Duncan, are you in Calgary? So 47% think it runs slow, 37% think it runs fast, and 19% think it runs normally. So it wasn't normally. My idea here, I mean, it will be close to normally, right? But the idea here is that as you get farther away from the center of the Earth, then gravity decreases a little bit. So instead of being 9.81 as it is at sea level, it might be 9.80 or something like that. Just a slight, so slight, oops, sorry, slight decrease in G, okay? G is on the denominator, so that means slight increase in T. So instead of going tick, 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 it goes tick, 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 a little slower. And so that's going to call it a slow clock. So what that'll mean is that you'll be late for work, right? Or it'll keep losing time. So it'll really be 11:30, but your clock will say 11 o'clock or something. Maybe late for class. Okay, so that's that. So you have to recalibrate it when you get to calibrate by just changing the length of the pendulum a little bit to compensate for a change in gravity. So one of the things that actually Akina mentions is that when you're walking, your legs actually naturally act like a pendulum. The motion sort of repeats itself. You obviously have muscles in your legs, so it's not exactly like a pendulum, but a comfortable walking speed is related to pendulum motion. Okay, so your leg can be modeled as a simple pendulum with the length equal to the distance between your hip joint and the center of mass, which is about ½ a meter. And so the frequency is around 0.7 hertz. And this is, remember, F is equal to 1 over T. So the equation for frequency is 1 over 2 pi times the square root of G over L for a pendulum. If you have longer legs, you'll have a lower frequency of your walking pace. So for example, a big giraffe or something will have fewer steps per second than a human because of their long legs. And a small dog will have, if you watch those dogs walk along, you can see their legs with a very high frequency if you compare it to the human that's right beside them. Okay. So the biological side of this. In the clock example, I think G decreased a bit because you're going to higher, yeah. Yeah. Well, I'm just going to leave that on in case most people complain. Okay, here's a little example problem. Luke and Leah have a combined mass of 120 kilograms and both grasp a rope of length 30 meters that is attached to a beam above them. The beam is halfway across a 10-meter horizontal gap. So this is the basic idea. I'm talking about the movie Star Wars, and these two people are, it's like the original Star Wars movie. This is a terrible little drawing there. They are over here on one side of a gap. And so typically in these movies, there is some sort of big chasm and there's no handrails. You know, you could just fall. So they don't want to fall. So what they want to do is swing across and go over to the other side. And the reason is because there's some stormtroopers that are shooting lasers at them on this side, and the exit is this way, right? So exit. They're trying to find their spaceship or something like that. So they need to go across. You got me? The question is, if they start from rest and swing down and up, just reaching the other side, how long does this take? And I'm going to treat this like a simple harmonic motion question. So this is a simple pendulum. Okay. And then this L is equal to 30 meters. We know that. Then what else? The mass we don't know. I don't think it matters. But mass is we do know is 120 kilograms. But again, I don't think it matters. And this distance from here to here is 10 meters. So what I'm going to do is assume simple harmonic motion. We can check this at the end by checking to see if it's small angle approximations. But so back and forth forth both ways would be 1 period. Okay, across once, we'll take the period over 2, half a period. Make sense? So all we have to do is say that t is equal to 2 pi times the square root of L over G. I guess we'll assume they're on Earth, even though it's a Star Wars movie. Let's assume that G is equal to 9.80 meters per second squared. Maybe it's artificial gravity set to be that way. Anyway, you get me. So the time is going to be t over 2. So it's going to be just pi times the square root of L over G. So t is going to be equal to 3.14. I have to use lots of decimals there, 30 over 9.8. So I typed that in my calculator, I got 5.5 seconds to swing across. And let's just check, by the way, if, so in this case, if straight down is theta equals 0 degrees and theta max is like the amplitude or something like that, this thing, then I think we can find what that is by, we could say here is 30 and here is 10 over 2, right? Which is 5 meters. So if you look at this theta max, I think that sine of theta max is going to be equal to 5 over 30. So theta max I got is equal to 9.6 degrees. So that's kind of high, but it's less than 10 degrees. So simple harmonic motion is okay. Just to check there. And the idea is that Rubena was asking, why is it t over 2? So the period would be how long it takes for them to get from the side they don't want to be on and all the way across and back again to, again, where they started, right? That's 1 period of simple harmonic motion. And they're no closer to the exit than they were at the beginning. So what they want to do is hop off when they've only gone half the period. Make sense? And they're the simple harmonic oscillators. Yeah, and SHM is, everyone's going to understand what that is, the markers. It's good short form. Okay, I think we got another poll question coming up. Okay, so a 1 kilogram mass is attached to a horizontal spring with a spring constant of 1 Newton per meter. When the mass is at x equals 0, the spring is in equilibrium. Then the mass is pulled to x equals plus 1 meter, and it's released from rest at a time t equals 0. This is my Excel spreadsheet from last time. The question is, at what time does the mass reach a position of x equals -1 meter? It starts at plus 1, gets down to -1. How much time should that take? Here. I have to think about this. Some number of seconds. Get you guys started. This is going a little slow here. You guys following this? Just drawing a little bit of extra help on that thing. Okay. We'll vote in, see if you remember this, and then I'll go through the answer. 10 seconds, please. Okay. Survey says 70% of people who voted are voting for C, T equals 3.14. So that was the whole thing that actually happened, if you remember last time. The answer is C. When I was looking at the Excel spreadsheet, problem is I didn't, on Google Sheets, I could only get 1,000. So, but the basic idea is the period is 2 pi times the square root of m over k. M is 1 kilogram, k is 1 Newton per meter, so it's 1. So it's 2 times pi seconds. So this is 2 pi over here, where it goes back up to the beginning. So halfway will be at pi seconds. Okay. So it's 3.14. So, and I just wanted to show you, so if you look at where the these slides are on my Monday, Wednesday, Friday slides on the Quarkus, you can see I've also posted a link to a big Excel spreadsheet, which if you want to load it in, what I did with it is I couldn't copy and paste more than 1,000 rows on my Google Sheets, but you can do many, many thousands, hundreds of thousands on Excel. So it's the exact same thing. I just took these equations, x, final is x initial plus v times dt, but I made dt to be 0.00001 seconds. So when I did that, the minimum, if you look at this, turns out to be right here, negative, like the most negative it gets, happens to be right at t equals 3.14159 seconds. So I just wanted to prove to you that with these very, very simple equations, a equals negative kx over m, and these equations, you do really get pi. So it's, again, it's this kind of beautiful, weird thing here. It's a way of calculating pi. So. Weird. Okay. I think that's it for. Yeah, I would recommend, I guess, if you're going to use this equation, x equals a times cosine 2 pi over t, you have to have your calculator set in radian mode. And yeah, if you had, so this, by the way, this, someone's pointing out, this whole equation, x equals a times cosine of 2 pi over t, that assumes that you're released from rest at maximum value of x, okay? It assumes something about the initial conditions. If you start with a kick of some initial velocity at x equals 0, then you might use x equals a times sine of 2 pi t over t. Okay. All right, so simple harmonic motion, it's we've sort of finished that. Now I'm going to spend the rest of today talking about two different kinds of harmonic motion, damped and driven. And neither of them are simple, there's something different about them. And the thing about simple harmonic motion is that if the net force on an object is just a linear restoring force, some negative constant times the displacement, then the position as a function of time is this x equals a, depending on the initial conditions. If the initial conditions are just right, a cosine 2 pi over t times t. The thing is that cosine, if you look at it, it goes on forever. It started, infinity that way, and it goes to infinity that way. So in real life, motion like this never lasts forever, because due to friction or some kind of dissipative forces, all oscillations eventually slow down. So this is the phenomenon of damping, which is that the amplitude of a real oscillation will decrease with time, and that's called damping. And so it's important in real life. You have something, there's actually different classes of damping. There's 3 different classes. A weakly damped system is one that continues to vibrate for many periods. And what we call these dashed lines right here is called the envelope. Okay, so envelope is a steadily decreasing function. It's usually exponential, actually, function, which decreases the amplitude. So what you say is that the amplitude is equal to the initial amplitude times the envelope, which is envelope of some decreasing function. So it gets less and less. In an overdamped system, the vibration takes a long time to return to equilibrium, and it never actually does. So if you really increase the damping a lot, it just approaches zero. And in a critically damped system, the vibrating object goes back down to zero just once as quickly as possible. And so I think that's all I really wanted to say about this. And so when you, for example, design the shock absorbers in a car, you try to critically damp it. So you've got these springs, which are holding up the mass of the car. If you had zero damping in these springs, then every time you hit a bump, your car would go boing, go boing, go boing, go boing for a long time. So what they do is they fill the springs and the shock absorbers with a very viscous oil. And what that does is it slows down the vibration to try to critically damp it. So you return back down to normal in sort of the shortest amount of time. So I do have a poll about this. Let's see what you think about this one. It's the kind of question you might get asked tomorrow. The question is, what can you ask about damped harmonic motion on a midterm? Let's say you have a 0.5 kilogram cart attached to a horizontal spring, the other end of which is attached to a fixed bumper, like a wall. So this is mass of the spring. The spring constant is K equals 150. The cart is pulled to the side and released from rest when the spring has been stretched by 0.035 meters. How much mechanical energy is converted to internal energy before the cart stops oscillating? I just need to use my calculator to get this one here. Let's give another 15 seconds. Maybe we'll leave the polling open for a little bit while I start discussing this. So the idea is that all initial energy is dissipated, right? So all you have to do is find what the initial energy of simple harmonic motion would have been. So you just use E is equal to 1/2 K A squared, or 1/2 M times V max squared. But you are given K and you are given A. So definitely use this one. Remember those two equations? So the idea is it starts off as a simple harmonic oscillator and then the energy is just dissipated. Okay. So it's 1/2 times 150 times 0.035 squared. Let's see who got it. Yeah, and when I worked that out, I got my calculator 0.091875 joules. So great job, 65%. Be all set for tomorrow night. Josephine, how you doing?
Hi.
Hi.
I know this is probably far back, but can we go back to the one with the child on a swing?
Yeah. Remember that one? That was a weird one. Just remember, we're going to go to 19 next. This one?
Yeah. So you say that the L decreases as the child stands up.
Yeah.
Why is that? Because the way I see it was her center of mass is getting like higher, if that makes sense.
Yep.
So I thought it would be increasing.
So L is the length of the pendulum. So you got to think of the child as a pendulum, where the top of the string is fixed to the ceiling, or fixed in this case to the top of the swing.
Right.
And L is the length of the string between where the fixed point at the top and down to her center of mass. Can you picture it?
Oh, I see. Okay, so it's from the top
Yeah.
of
Down.
the pendulum to her center of
Yep.
mass.
Yep.
Oh, okay. Thank you.
Yeah, you got it. Okay, good. So trouble with PowerPoints that, I remember I was always like looking at the slides behind where the professor was. These things disappear. What did I say? We're on 19, right? Okay, driven, yeah. This is weird. So actually we have a demo here, which is going to put a ticking sound, but here's the idea with driven oscillations and resonance. Consider an oscillating system that when left to itself oscillates at some frequency, which we'll call F0. We call this the natural frequency of the oscillator. Then we suppose that the system is subjected to a periodic external force. And this external force has its own frequency, and we'll call that F external. That's called the driving frequency. Driven systems oscillate at F external. The amplitude of oscillations is generally not very high if F external differs much from F0, but as it gets closer, the amplitude of the oscillations rises dramatically. So I'm glad Josephine just asked about the swing, because I was just about to talk about that. If I am pushing my child on the swing, then what I am doing is applying an external driving force to the child. And so you can imagine that I could push the child really rapidly, just keep on whacking her on the back, and she's going to get pushed around a little bit, but she's not going to go very high. I could also push her once, go on my phone, once, 5 minutes later, and a low frequency, again, she's not going to go very high. What I have to do, and it's very easy to do, is I have to match my external frequency of input energy to be the same natural frequency that the child has if they were swinging without any driving force. And the way you do that is you just stand off to one side, and every time the child is close to you, they've gone through one period, so you give one push. And if you do that and just keep pushing, then the child will eventually get higher and higher and higher. And that's called resonance. And the way it looks, if you graph it, is there's F0, there's F external. The amplitude goes up to some maximum at resonance. So you want to see a kind of messed up demo? This sort of has something to do with this. Just what I want to do, I'm going to stop the share here. Turn it around to the penguins. There they are. Okay, so we have 4 happy little penguins here, and they're all set to have the same frequency of oscillation. So what do I have to do here? Push these up, I think. Or no, yeah, put it down. There we go. 1. Yeah. I already messed this up. Personally, I don't know what I'm doing here. Oh, there we go. Let's push them in. Okay. So these penguins all have the same frequency, we hope, but they're all a little out of sequence with each other. They're not oscillating together. And so but they're mounted on this on these tin cans, so they're all sort of connected to each other. So these can kind of resonate together. So I think we're just going to leave these and check in on them after a little while. The only thing I worry about is that I think I adjusted one of them a little. Okay. Screen 2. Okay. So getting back to my slides here. Feeling road vibrations in a car. So if there are some equally spaced bumps in the road every 10 meters, and the natural frequency of the shock absorbers in your car is about 0.9 hertz, at what driving speed will you feel the bumps the most? Do another poll here. That ticking is going to go for a while. Hey, just have to interrupt you guys to show you what's going on here. They've come into resonance with each other. So they're all now oscillating with in the same way together. So they started off with all sorts of different phases, but now they're going together because they're all kind of connected. So that's an example of resonance. And we'll stop the ticking and we'll stop the poll. Oops. Everybody, let's do poll. Share results. So 41% of you were voting for C. So let me see what I think there. Let me bring up the chat again. Okay. So yeah, I think what's going on here is that for resonance, set the T, if you're going at some speed V over some time T, equals to T, the sort of the resonance frequency of natural oscillations of your shock absorber. So V is equal to D times 1 over T, D times the frequency, so 10 meters times 0.9 hertz. So I think that's the 9 meters per second. That's exactly the speed you don't want to drive at if you don't want the amplitude to get higher and higher as you hit these bumps. Okay. And the idea, Mircea, is that these penguins were all set to have actually the same frequency, but they were just out of phase with each other. So they started at different times. But I guess what they do is they just adjust each other's frequencies just slightly because of this resonance. They're being pulled towards this particular frequency until they match themselves up and then they come into phase with each other. So this is sort of a mix, this question, isn't it? It's looking at very, very old equations for constant, constant velocity and mixing it with this new idea about resonance, where you're matching the frequency of a driving oscillation, which is the bumps in the road, to the natural frequency of 0.9 hertz, which is the simple harmonic motion of these shock absorbers. Okay. I think that's kind of it. I guess the other thing is I can just say that if you look up Tacoma Narrows Bridge disaster on YouTube, you'll see that there was an actual bridge which had a natural frequency. It was one of these suspension bridges, had a natural frequency. And then what they didn't know is they built it over the Tacoma Narrows, and because of the way the wind gusts through there, and actually the way it blows around the natural structure of the bridge, the wind had a frequency to it. So it was a periodic gusts of wind that were coming through there and going around this bridge. And what that did is it set up a resonance with the natural frequency of the bridge and the wind. And people used to drive over this and say, wow, this thing's really swinging around a lot. And they called it Galloping Gertie. And then, a few months after it built, the whole thing collapsed. So that's bad resonance, I guess. A little bit of time left, 4 minutes. Let's talk a little bit about tomorrow night's test. You haven't forgotten about that. Remember that there's 5, this is the 5th one. And depending on X, they're worth between 10 and 12% of your final mark in the course, because we're dropping the lowest final assessment score. So if you're really, really happy with your first 4 midterms, then there's really no reason to do the test tomorrow. You can take the 0 and it won't count against you. But you may as well do it. It will become available on Quarkus to start at 8:10 tomorrow evening. So be ready. So like 32 hours from right now. If you are registered for the alternate sitting, then you do the whole thing exactly 2 hours later at 10:10 p.m. Toronto time. If you miss the assessment, that's okay. You get 0, but if it's one of the ones that doesn't count against you. The assessment is open book. Allowed aids include your course notes, the textbook, these videos, Google searches for static web pages, a calculator, Excel, Python, etc. However, you must work on these assessments individually. You can't have group work or chats with other students during the assessment. Okay, that's the rule. Once you start, it starts a 30-minute timer, and the assessment ends either when the 30-minute timer ends or 8:45 p.m., whichever comes first. So if you don't start exactly at 8:10, if you start at 8:12, you still get the full 30 minutes. But if you start at 8:16, then you'll only get 29 minutes because it'll stop at 8:45. You'll see one question at a time in a random order. You know this. You submit each answer by clicking next and see what you see in the next question. You do not have the ability to go back and change any answer after it has been submitted. After completing all 10 questions, you have to click submit quiz. You're obviously going to need a calculator to do the numerical things. New feature. So this comes from actually a suggestion from one of you in the chats. Someone suggested, why don't you give a little suggestion of how many minutes each one should take? So I did exactly that for tomorrow's test. Tomorrow, every question will start with a time estimate, which is between 1 and 5 minutes, depending on the amount of work involved. 2 of the questions, I put 1 minute. 4 of the questions, I estimated 2 minutes. 2 of the questions, I put 3 minutes. And there was one question I thought 4, and one was 5 minutes. Although I think the 4-minute question, it's just because there was a lot of reading involved. There wasn't a lot of calculation. It was a very wordy question. So it took me a long time just to read it. But anyway, if you add all these up, you get 25 minutes. So if you follow my time suggestions for all of these, then you'll still have 5 minutes left at the end. So for every question, the first thing you'll see is it'll say estimated time, 2 minutes. If your first question you get says estimated time 5 minutes, well, then that means you got the hardest question first. So you should definitely take some time and go through it. If you get 1 minute, then that's more of a conceptual one you still got that 5-minute one somewhere coming along. You can take any amount of time you want, right? These are just a suggestion, just an estimated suggested time. You can take longer or shorter. But I mean, you don't want to run out of time, right? And everyone's getting these questions in a random order. So I thought it would be useful to have a little time estimate. And I hope it doesn't stress you guys out. You can always just ignore it and do whatever you've been doing. But if you find it helpful, then great. If you think it's not helpful, just please ignore it. Okay. All questions are multiple choice. They'll be marked automatically, so you don't have to wait too long for your marks. I will talk about them on Wednesday morning. Material is all from chapter 9 and 10 from Etkina. Also, keep in mind stuff from chapters 2 to 8. Remember that bump in the road question, for example, that's really kind of a chapter 2 equation, isn't it? But it's applicable. There will be at least one question based on your practical 4. Okay. That was sent to me by your TAs. I think that is it. So when we come back on Wednesday, we're going to be talking about waves. And here's a question for you to think about. 2 of the 5 senses depend on waves in order to work. Which? So good luck tomorrow night. I will be right back here in the lecture Zoom room tomorrow at 8 to in case you have any questions or something like that, you can type them in the chat or something like that. Okay, so good luck, and definitely see you on Wednesday morning, I hope.